If you recall, one of the problems that we had in the past concerning double integrals, and I don't know if I've ever finished, I just kind of like, here's a problem, and then like walked away from it, was to describe these two regions. First is just the quarter circle, quarter of a circle of radius 4 in the fourth quadrant, and then the quarter circle of radius 4 in the fourth quadrant, but with the without the part where x is between 0 and 2. So we're cutting a vertical strip off of that quarter circle and writing a double integral for that region. All right. We want to set up double integrals to describe this region. Now, we could use those double integrals to find the area of each of these regions. That would be helpful. Once we calculate the area of the regions, we can find out if our integral is describing the correct area. But the focus of the problem is to be on writing the double integral itself. All right. So first, if we just look at the double integral over here, if we make a dx dy integral, this would be the easiest one. This will be pretty easy to set up. It would be messy to integrate because we're integrating round things with square coordinates, but setting up the integral is pretty straightforward. So one way we could set this up is the integral as y goes from 0 to 4. So here down here is, sorry, negative 4. Yeah, thank you. I was going to dy dx, and then I started to write. So the y down here is at negative 4. And the y up here is at 0. So if that's my last integral, I'll integrate from negative 4 up to 0. For a typical y value, I need to see what x is between. X starts here at 0 and ends at the circle. So x starts here at 0. Going all the way to 4 would make a rectangle, but we want to end at the circle part. So x goes from 0 to, since I'm on the positive x's, the positive square root of 16 minus y squared. Whatever the function happens to be. And we've integrated this dx dy. From here, it'd be really easy to translate to the truncated portion of the circle because we're just describing what x is between and what's y between. In this problem over here, we could set up integral of y, and then an integral of x. So if I set up the dx as the inside integral, I would have to change my lower bound on y. I'd have to figure out what y is down there, but y will end at 0. That's the same. So y stops at 0. X, for those typical y values, x will start off at 2 and end at the circle. So x will start off at 2 and end at the circle. To describe the circle with an x, square root of 16 minus y squared, or as a function of y, as an x equals. But notice that I don't want to integrate this all the way from negative 4. I don't want to integrate from negative 4. I want to start my y down at that lowest y value, which happens when x is equal to 2. So we're doing the same thing up here by rewriting this equation to say x equals plus or minus the square root of 16 minus y squared. If I plug 2 into my expression, I want, in this case, the positive square root of 16 minus 2 squared. 16 minus 4 is 12, so the square root of 12. That's where we're going to start down here. So the x will go from 2 up to the circle, and the y will start at the negative square root of 12. And go up to 0. So here are some integrals dx, dy. In the first go of this integration, we're going to end up with terms where we have to integrate if we want it, if f of x equals 1, that will give us the area of these regions, and we would have to integrate the square root of 16 minus y squared. So we would have to integrate using trigonometric substitution if we were going to be doing that by hand. We can also set both of these regions up as dy dx integrals. We can also describe these regions with dy dx integrals. In this case, we should start with the constants as usual. And we'll say here, the x goes from 0 to 4. So we're going to have to integrate from 0 to 4 dx. That has to be constants because that's my last integral. For a typical value of x, we're going to go from the bottom, which is the circle, up to the top, which is the line y equals 0. So in this case, if x squared plus y squared is 16, then y is plus or minus the square root of 16 minus x squared. And we want the negative because we are below the x-axis. So we'll start off at negative square root of 16 minus x squared and stop when y is 0. Lowest value, highest value. This first integral gets us that round part. The second integral gives us all of it from left to right. All of the quarter circle from left to right. Once again, this would be bad to integrate, or just messy to integrate, but easier to set up because our boundaries are just these horizontal and vertical lines. In the truncated version of the circle, we're going to integrate from x equals 2 to x equals 4. Then for a typical x value, the bottom is at the circle and the top is at 0. So the bottom is at the circle and the top is at 0. In this case, we didn't need to do anything fancy with this square root of 12. We took care of that when we said x is equal to 2. That point down there is x equals 2 and y equals negative square root of 12. That's why we didn't have any of that fancy square root stuff going on for our constants, because we took care of that when with the x equals 2. We're using that constant. Right, this is right. So we can either integrate from 2 to square root of 16 minus y squared. That's our left to right. And then top to bottom, or bottom to top, negative root 12 up to 0. Or we can integrate the other direction first. We can integrate bottom to top, negative square root of 16 minus x squared up to 0 for the values of x between 2 and 4. I had this labeled positive. Any questions? Is everybody okay? We also wanted to find some double integrals in polar coordinates for these two regions. Polar coordinates are going to be great, especially for that first one, because this is just two intervals in polar coordinates. So this is very convenient for us on that first one. The second one, it's going to be less convenient because of that vertical line. That vertical line messes a lot of things up. For the most part, we can get away with just trading our coordinates. In this problem, we've got x squared plus y squared is equal to 16. If we just translate this into polar coordinates, that says r squared equals 16, which is just r equals 4. When we describe a circle, describing a circle in polar coordinates is just a constant function of r. So in this case, r is equal to 4. And that same thing is going to happen over here. X squared plus y squared is equal to 16. That we can just translate to r equals 4. What's inconvenient about this, describing this truncated region, is that we have a vertical line that is not the y-axis. So what we want to notice is that on a generic line, this region always starts off where r is equal to 0, and r always goes out to 4. So here is where r equals 0. And this whole circle, this whole quarter circle, is where r is equal to 4. So when we say r goes from 0 to 4, we're starting at 0 and going out to 4 along this line, and along this line, and along this line. That's where r is going from 0 to 4. But r is always going from 0 to 4. In this case, theta, if we restrict theta to go from 0 to 2 pi, then we want to start theta down here at 3 pi over 2 and end at theta when theta is equal to 2 pi. That's going, so we'll go from 0 to 4 for all the theta from 3 pi over 2 to 2 pi. The other thing that we have to remember when we're writing a double integral in polar coordinates is that dA needs to have that extra factor of r to turn d theta into a length. So our double integrals here will be very simple because we just have two intervals. I can integrate r from 0 to 4 and theta from 3 pi over 2 to 2 pi. I do have to include an extra factor of r for the d theta. I need that extra factor of r to turn d theta into length so that r d theta dr is area. since we just have two constant intervals, this one is easy to turn around. I can just go from 3 pi over 2 to 2 pi. And then r goes from 0 to 4. I'd have to rewrite my function in terms of r and theta. I would still need this extra factor of r to turn d theta into a length, but now I'm integrating dr d theta. In this case, the setup of the double integral is easier, and the execution of the double integral will also be easier because we're just integrating the function r. If we calculate these two integrals, we would want to make sure that they come up with the same value for each of these down here, and that those values match the values that we got for our rectangular integral. Difference is these I would be willing to calculate by hand to find an area with f of r theta equal to 1. And up here, I would not be willing to calculate it by hand. Actually, I personally would because it's trig substitution and that's fun. Over on the truncated version, the problem that we run into is that r is different for different values of theta. So here at this point, r is equal to 2. I spelled r wrong. This point here, r is equal to 2. And theta is equal to 2 pi. So that's that point there. R is 2 and theta is 2 pi. When theta is 2 pi, I want r to go from 2 to 4. But we're not measuring r from that point. R is measured from the origin. So if I go down here where theta is equal to 3 pi over 2, that's not part of the region. Theta equals 3 pi over 2 is not part of this region. The values for theta in this region do not start until we get to this point down here. This is our initial theta value. Now notice at this point, r is on the circle. So r is equal to 4. But we'll have to figure out what theta is equal to. Any questions? So whatever value we get for theta here, that's where our theta should start. Theta should go from here up to 2 pi. And then r should go from this value for a typical value of theta. We'll start r at this line and end at the circle. So r is going to start at the line and end at 4. Everybody see the complication here. The most important thing to recognize is that when we truncate a circle, we don't get a radius at that point where we cut it. We don't get a radius. When we draw things by hand, it's like, oh, this is just another circle, but it is not. In our eyes, it looks like another circle. We want it to be another circle, but it is not another circle. Because this distance is only 2, but clearly this distance is 4 from the origin. Any questions? Here's what we have. This x squared plus y squared equals 16. Just by trading our coordinates, x squared plus y squared equals r squared, that led to the equation r equals 4. We can do the same thing with the description of this line. This line here is x equals 2. That's the line x equals 2. If we remember how to convert from rectangular coordinates to polar coordinates, or from polar coordinates to rectangular coordinates, x is equal to r cosine theta. So what we'll use here is that x equals r cosine theta. We have that x is r cosine theta, y is r sine theta. And I can take that r cosine theta to rewrite the equation of the line. Just like we did down here. So here r is equal to x over cosine theta. Or we might write that as r equals x times secant theta. That's the description of the line. So for a given value of theta, the value of r will start at the line and end at the circle. Start at the line, end at the circle. One thing to note is that I want my theta to be the last integral because theta is between constants. So I'm going to go theta from this value down here up to 2 pi, while r, for a typical value of theta, will start at the line and end at 4. The line is described as x secant theta. Oh, sorry, r secant theta. Oh God, x is 2. So since x is 2 and x is r cosine theta, r is 2 over cosine theta. So r is 2 secant theta. So for a typical value of theta, that's going to be between whatever that theta is down there and the 2 pi. We start at the line and end at the circle. The line is described by 2 secant theta. And the circle is described with r equals 4. I'll have to write my function in terms of r and theta. I will need a factor of r to make the d theta into a length. We do have to figure out what that theta is equal to. That theta happens when r is equal to 4. We also know x and y, so we can actually get at using tangents. So using what we have in front of us, if we're going to have 2 secant theta equal to 4. So secant of theta is 4 2s. So cosine of theta is equal to 1/2. This gives us a reference angle of pi over 3, 60 degrees, or pi over 3 radians. We need to put that in the fourth quadrant. So that's going to be 1, 2, 3, 4, 5 pi over 3. So we're going to have pi over 3 in quadrant 4. So we'll start at 5 pi over 3 and integrate up to 2 pi.
So, right, oh yeah, you use like pi.
Right.
Pi divided 2 by
Right. The reason I wanted the theta, that the cosine of theta needs to equal 1/2, and I need to look for a theta between 0 and 2 pi, and I need the theta that lands in the fourth quadrant because we're looking at the fourth quadrant. There's also a pi, theta equals pi over 3, but that's up in the first quadrant and not where we're looking here. Any questions? Comments? How's everybody okay? Everybody looks so stoked. Like, oh man, I just cannot wait to crush this test on Friday. Oh, sorry, Thursday. Don't come in on Friday expecting to crush the test because you will have missed it. In this case, I would not ask for the integral in the other direction. R is dependent upon theta. Theta gets to be constant. Notice that our thinking was the same. We just had to apply some trigonometry to it, and that's what we didn't like about this. Notice that what was causing the problem was that vertical line, which polar coordinates will struggle to describe. Rectangular coordinates really good describing lines that don't go through the origin. Polar coordinates, not so much. Fortunately, in general, we have, if we just want to describe lines, we have vectors for that. How's everybody okay? Told you Calc 3 was the easy one. How much calculus have we done today?
about 6.
We wrote like some calculus symbols, right? It certainly looks like calculus, but how much calculus thinking did we really need? It all just happened in the background. All the calculus thinking happened in the background. This is just becomes a problem of what's x between, what's y between, what's r between, and what's theta between. So I guess you have a calc test on Thursday that doesn't actually have a lot of calculus on it, which is weird. But a lot of times in a math class, you'll be doing stuff that actually fits into a previous math class. Like when you were in trigonometry, think back to trigonometry. Everybody remember trigonometry? Of course we do. I'm not going to have a quiz on trigonometry beyond this. So they're like, oh, totally. In trigonometry, you had to verify trig identities. Make one side look like the other by hitting it with a bunch of identities, by throwing a bunch of identities at it. That was an algebra exercise. Just full disclosure, that was an algebra exercise. In Calc 2, you had to do partial fraction decomposition. That was an algebra exercise, an algebra that we didn't teach you in algebra class. We wait until calculus class to teach you about partial fraction decomposition. We can't do everything at once. We can't do all of algebra before trying to move you on to calculus. It would take too long. Any questions? Comments? All right, that's going to do it for today. If you have requests on problems, please let me know through email, or you can just tell me tomorrow if you want it to be a surprise. That's it for today. I'll see you all on tomorrow, but have a good day and thanks for playing.
Okay, so